Now we're going to be discussing the high voltage battery pack, but to get there we've got to cover some basics. Now this is a very important subject because customers are concerned about the durability and the health of the battery packs. There's been a lot of scare stories told about you got to replace all and they may run $3,500. That's not true. We can replace one at a time. But since one of the things we're going to be doing in this program is making sure you know 3 ways to diagnose this, we want to make sure we cover some basics so you've got some good basis. Now batteries are made up of a group of cells. A cell has 1 negative and 1 positive electrode. Now cells can be connected together in series or parallel to each other, and there's an important reason for doing this, because connecting cells in series increases the voltage output. Now to get power you need voltage and current. Power is voltage times current. So sometimes you're going to need batteries connected in series to get the voltage higher because you've got a limited current flow. And we'll talk about cases like that. Connecting them in parallel will increase the capacity, but voltage remains the same. Now we're going to make sure you understand that, but first let's get into battery technology. Let's talk about what a cell is and what a battery is. Quite often what we refer to as a battery is a group of cells. In this case we're looking at a battery we refer to as a brick, because we give you a good reason for it later on, out of a hybrid. It's about 5 inches high, little over 9 inches long. You see 1, 2, 3, 4, 5, 6. This battery has 6 cells inside of it. And remember, a cell is a pair of electrodes separated by an electrolyte. So that is repeated 6 times. And we'll talk about how they're connected together. But let's go back to something you're familiar with. You've seen one of these before. When you buy one of these, you're buying a 9-volt battery. Actually, you're not. You're buying 6 1.5 volt batteries connected together. Because when we open it up, we find inside all you bought were 6 little batteries connected together in series. Now, this is a low amperage battery. To get more power, they increased the voltage, hooked 6 of them in series and got 9 volts. This has 9 times the power of a 1.5 volt. Now we could have collected them in parallel and had 9 times the current, but would still only have 1.5 volts. And 1.5 volts was too low to run the circuitry this was designed to run. There's a reason for all of these choices, series and parallel. Here we needed voltage to increase the power. So the power is 6 times higher than the individual battery. So as you look inside, you see these bus bars. Bus bars in a hybrid look quite a bit different, and they're much larger. Over here, to the left, you see them. There's a quarter to give you an idea of the size of them. They're quite a bit thicker, larger, and much stronger because they're going to carry hundreds of amps. So what we got on the right is a battery that carries milliamps. On the left is bus bars for 100 amps or so. Here's our batteries. Here's 2 of these bricks. These 2 bricks can be put together to make a block. And a block is what we're going to read in scan data. And we keep referring to things that try to make sense to keep them getting confusing. But let's look at what we've got here. We've got spacers for airflow between the batteries. We need to keep these batteries cool. We don't want them getting hot. Their battery life will be shortened if they heat up. And these are very high amperage, 150 amp batteries. Yes, 150 amps I said. They have vents in case there's outgassing from some heat and other things. We want to vent it out. In case there's a little bit of overheating, we don't want the corrosive electrolyte inside here to get escaped, so we have a vent there. And in the front, this large bolt, this one in the back just like it, this large bolt is where we connect in. The reason it's so large, the reason it is quite big, is we're going to be doing about 150 amps. But let's talk about how we're going to do that. We're going to connect these batteries in series. All the cells inside are in series. And then we're going to connect these in series to increase voltage. Since we have 150 amp batteries, we want to get the voltage higher. And to get the voltage higher, we're going to click plus to minus to plus to minus to plus to minus, right on down, and increase the voltage. Notice the air spaces. We have room in here for air to cool these down. Let's look at some other batteries. Here's the top view. Here's the vent we were talking about at the top. The vent's there to save the gas, and we're going to pull that vent out through a tube so it's vented outside the vehicle. We want to get anything corrosive out of this battery compartment. So if there's a little bit of anything in here that would be corrosive, we're going to vent it outside the vehicle. Here's what it looks like when we put them together. We've removed one of the nuts so you can see it sitting here. Look right here on the left and you'll see the power bus where we've removed one of the nuts. Those are large bolts holding in place. But you also see some small wires here at the bottom. This is where we're going to read scan data. Notice of these batteries, there's only one small wire for each set of these batteries. A pair, a block. We're going to be reading a block. So if it's 7.5 volts for a brick, when we put two bricks together, it's 15 volts. And that's typically what you see in scan data. Now the big black lead out of the bottom is the orange wire going out. And now here's how we show cylindrical cells. There's several type cells, but it shows a good example of how they're hooked in series. Through this tube, there's a number of batteries hooked in series. Output current must flow through all of these batteries, so the rating of each cell is going to rate the current flow. Let me say it again. The output current must flow through all of the batteries in this whole battery pack, so the current rating of each individual battery is the rating for the cell. This whole battery pack is going to be rated by what one cell can carry. Now this is important to us for diagnostics, because if they're all in a series and one of these batteries is not as good as the rest, it's going to stop things from working. So it's very important you understand this. Let's go look at this. Here's our two batteries hooked in parallel. We've got some strange looking bus bars, some to contact the bottom on the right, which have big buttons, and some to connect the flat sides, which have no buttons. And that's the negative and positive, like you're familiar with flashlight batteries. But what's going to happen is the current is joined at the output terminals, so the current rating is equal to the current rating of each cell times the number of parallel cells. Now we have a 1.2 volt battery here at 150 amps. This is the kind of rating we're getting out of a cell in a hybrid. Not a typo, we are saying 150 amps. So what we wind up with is 1.2 volts at 300 amps. Now we've doubled the power, but 1.2 volts is not very much voltage. If the voltage stays low, the current has to become excessively high. If we want to get any real power out of 1.2 volts, we're going to have thousands of amps. That's not practical. So what we're going to have to do is take these high rated cells and put them in series, because when we put them in series, the output voltages increase. Let's see what we're talking about here. The current is unchanged because current flows through each and every one of these cells. And remember, if one of these cells is not conducting fully, you're not going to get full output from the battery. The output is 2.4 volts, but it's only 150 amps. And it doesn't matter how many cells are hooked in series, it's always going to be 150 amps. But I've got nice high amperage in these hybrid cells, so what I need to do is connect a lot of them in parallel. High voltage packs in today's hybrids use nickel metal hydride. They're good batteries. They've been used for a long time. In this particular case, they use an alkaline electrolyte to conduct ions between the electrodes. But here's an important point. The electrolyte does not take part in the reaction. You say, what does that mean? Here's what that means. In a lead acid battery, we change high sulfuric acid into water as a chemical process during discharge. So the electrolyte is changing from water to sulfuric acid as we charge it, and from sulfuric acid back to water as we discharge it. Here, the electrolyte does not take place in it at all. It's just a conductor. Now keep in mind, there's a key word I said there. It is a conductor. We're going to measure that later on. Since it doesn't take part in the reaction of discharge and charging, it is going to give us a good long life. It takes none of the reactions during charging and discharging, remains the same. This makes the voltage output very stable as the state of charge is varied. Now it changes slightly, but nothing like a battery that we've been used to using. Whereas we go to a low state of charge, we drop several volts on a lead acid battery. We'll drop tenths of a volt on a nickel metal hydride battery. Now electrolyte leaks must be neutralized with a mixture of vinegar and water. Yes, this is not soda and water like you're familiar with, because that's for an acid battery. This is an alkaline battery, and we need vinegar to neutralize the alkaline. The electrolyte is extremely corrosive if it's not neutralized. We're going to say it several times. Have you ever had an alkaline battery go leak in a flashlight and try to get that flashlight to work again? I asked a group of people this a while back, and they said, yeah, there's an easy solution to that. Send it back to Maglite and they'll replace it. That's right. You're going to have to do something bad. Let's look at how they construct these. We said this is a 150 amp battery. How in the devil do you get a 150 amp battery? Well, we take sheets of electrodes. We have one of them as an anode, one of them as a cathode. We separate them by a nylon separator, and we fill this cavity in between with electrolyte. There's many, many, many square yards. There's hundreds of feet of foil rolled into a roll to make one of these cylindrical batteries. Here's what they look like when we get them put together. When we put them in the battery pack, we put them in the battery pack so they can all be wired in series. Each tube is wired in series. Now, as we go down and look at the bottom, you see a tube laying there. It's called a battery stick. That's your 7.5 volt stick. There's a single battery, and right beside it is a D cell. In a D cell, we can get about 1 amp and 1.5 volts. In this hybrid battery, we get 1.2 volts and 150 amps. Since they're high capacity for amperage, we need higher voltage. We connect them in series. But don't worry, we're going to show you how we go through and look at the information in these so you can see them. Now, the prismatic battery is the square one we've been looking at, the rectangular one. It has many, many layers of positive and negative plates separated by a separator. If you've seen the inside of a 12 volt battery, it's got plates. These plates are much closer together, much more dense, and we're going to hook them together over here, as you see to the right, so that we take one cell like this, put 6 of them together, and have as a brick, and we're going to hook them together with large, heavy-duty bus bars. So what we've seen so far is we have 2 types of batteries. We've got the prismatic, rectangular ones on the right, and we've got the cylindrical on the left. The new Fords, Toyota, and Nissan use the one on the right, the prismatic. The Ford Escape, Merida, and the Honda use the one you're looking at on the left. It's the same thing, just 2 different approaches. It's how you package your cells. But the potassium hydroxide is used in electrolyte, and it fills the cell to act as a conductor of ions between the electrodes. So what happens is the negative electrode is connected to the case of the cylindrical cell, and the positive electrode is connected to the connector protruding from the top, the button of the cell, like we do on these cells. We cannot say enough that potassium hydroxide electrolyte is very corrosive. It can be easily neutralized with vinegar and water. The normal nominal voltage per cell is 1.2 volts. That's the voltage as it's constructed when it has been sitting for a while. This is not a number you're going to be using a lot except for some calculations. So don't get too tied to it. Battery voltage remains very stable between the state of charge of 20 and 80%. Now, you're going to hear some numbers about percentages in state of charge, and this becomes very important. This 20 to 80 is not the max usable. That's where the voltage is stable. Operation outside the 20 to 80% level will result in increased heat, internal battery pressure. Pressure venting may occur. You saw the vents, we talked about them. This is the maximum operating range and is not the normal operating range. If you operate at the maximum operating range, you will shorten battery life, and that's what no one wants. So the batteries are deep cycling like this will definitely shorten the battery life and may damage the cells. So we don't want to go to that 80 to 20. It's got to be a safer, more better range. The control systems manages battery loads, that's charging and recharging, temperature, to maximize battery life. And there's a very good reason for this. We'll talk about it. California and some other states require a 150,000 mile warranty on these batteries. That's a long time. And that's to ease the customer's concern about the battery pack. It originally started at 80, went to 100, and is now 150. Reason it's going up is the batteries have proven to be very reliable by and large. We do have a few accidents with them every now and then. But the state of charge and temperature must be controlled in a much tighter range than we've been talking about to reach the design objective of 200,000 miles. This computers and control systems will do anything to protect this battery. A safe discharge voltage for a cell is 0.9 volts, which is 75% of the 1.25 volts, which turns out to be 5.4 volts of a typical 6-volt cells, 10.8 for blocks. Why is this important? Because the bricks, a brick here would read a minimum of 5.4, but scan data will show us 10.8. Why is scan data so important? We don't have to put on rubber suits, rubber gloves, face protection to measure scan data. This is already built so you can measure 2 batteries at a time. When we have several hundred batteries in here, but you can measure 1 pair at a time with scan data. Several hundred cells. We're only going to have so many blocks and so many bricks. A typical Toyota second generation Prius is going to have 20 blocks of scan data at 15 volts. That's 300 volts it's going to be putting out. What would it be if we took 75% of that? Well, if we look at that battery and break it down into 75% of the charge, nominal charge, we could find out what it would be. But we're looking at the nominal 1.2. That's when it has not been charged. We're going to talk a lot about charging and voltages. Discharging below or beyond the 0.9 volt point, below 75% of the voltage, not state of charge, 75% of the voltage, can damage the cell permanently. We're probably damaging a battery that puts out 150 amps. And since they're all in series, you may be damaging the whole battery pack. Now here's what voltage and pressure look like. We've got the voltage is in red, and we're showing the 1.2 volt line in green. As you see, cell pressure is fairly low till we get out at the high end. We'll talk about that. Overcharging causes internal pressure to rise quickly, that's the blue line, and produce overheat condition and venting. It's not a good thing. What we're going to be using a lot is the typical middle of the range 60% charge. Yeah, we're not going to use 100% charge, guys. We're going to use 60% charge. Gives us good battery life, keeps voltage relatively constant. Right there in the middle, we're at about 1.2 volts. We're going to be using that when we do an engine off, stop, look at the battery. That tells us it's been charged and it's got a normal state of charge, somewhere close to 60%. What you don't want to do is go to, when we get past 80, somewhere between 80 and 100, depending on the battery and depending on temperature, we start outgassing and voltage starts rising quickly. It's a lot of heat, a lot of power. This is why we have the vent system in here. It will go out the vent tube, but we do not want this venting. The cell voltage drops very low over here, below 20%, causes excessive current flow, and generates excessive heat. Heat is the enemy of this battery. We do not want to be anywhere near the 80 to 20% range on normal operation. We want to keep it well inside of that range. So we're going to have a typical target range right here in the middle. Charging is stopped at about 68%. That's as high as it wants to go in state of charge. Doesn't want to go any higher than that. And you can see we keep everything stable and flat. And discharge rate, we'll keep it above 50% state of charge for normal operation. So we're looking at 50 to 68% is a normal range. This is a safe operating state of charge. It'll give us good battery life. And you'll be seeing this in scan data. This is everything we're talking about is in scan data. The purpose of this class is to get you to the next class to thoroughly analyze all the scan data. This is the tip of the iceberg on scan data. But all these numbers we talk about are important. Here's how we use state of charge for diagnostics. At 6% state of charge, the computers will shut down everything. It will not allow it to go beyond that. At 35%, the electric traction motors are shut down. We'll run strictly on the internal combustion engine. At 40%, the electric traction motor is reduced. It's not going to have full output because the state of charge is too low. At 50%, the internal combustion engine starts to recharge the high voltage batteries. Even if you're sitting at idle at a stop sign, whatever it is, it is going to restart this battery. And 50 to 68 is our normal ideal operating range. Now, as we're going too high, regenerative braking, where we're recharging the battery, is going to be stopped at 80%. We won't let it go above that. It lets it go a little above the normal range because regenerative braking is so important. At 94%, we're going to shut down all vehicle operations. We're not going to let it get into that outgassing, high temperature operating mode. So this is how you use scan data. We're really going to use state of charge, and it's available in scan data. When you pick it up and you look, you're going to be looking, is this battery between 50 and 68%? That's one of the first things you should look at in scan data as you start looking at it. Now, obviously, we're going to look at codes first because we need codes, guys. You will be absolutely lost without codes on a hybrid. But then you're going to have to start looking at what's going wrong. Before we start disassembling things, even with a code, we're going to read scan data to know what to disassemble. Remember, when we disassemble now, it's rubber gloves, it's face mask, it's safety precautions, it's roping off the area and putting up things saying you're working on a 300 volt system that can hit you with up to 200 amps. That's a lot of power. 60,000 watts. We're not dealing with something simple and small here. It's nothing like house current. You only got 30 amps available in the big circuits and 20 amps in a regular household circuit at 120 volts. That's not a lot of watts. We're talking far more than house voltage. So what we're going to be looking at as we look at scan data is we're going to watch this controlled voltage going up and down. It'll go up when we charge it. It'll go below when we discharge it. But it's going to keep it in a safe range and keep it out of the red zone. Overcharging or undercharging is a red zone that the vehicle is going to do everything in its power to keep this vehicle, the battery, from going in that range. It's not going to keep it dead on 60% state of charge, but it's certainly not going to go outside the 20 to 80 range. Now, these batteries have to be monitored by the controller to keep temperature controlled. And the good news is they are reported in scan data. we're going to beat you up continuously about scan data, because we're going to use scan data to keep you safe. That's important to us, should be important to you. We're going to have cooling fans that are going to come on, keep the battery in a safe range. They're going to be, this is a little more complicated than a simple on-off fan. You'd be surprised how complicated these are. In some vehicles, like the Ford Mariner and the Mercury Mariner and the Ford Escape, we're going to turn on the AC if necessary and have a special evaporator just for the battery pack. It may turn the AC on even though the customer hasn't requested it. Here's some of the overheat conditions that will show up in codes, because code's going to be important to us. Now here's something to look at. If you look at this, you see battery module, battery pack, and battery cell. We have a problem with the way they use this. We're not measuring battery cells ever. We're measuring battery bricks, which is a group of cells. But it's the term they used. We've got battery pack, battery modules. Now this is a composite of overheat codes released to the EPA as official codes. We have a big problem with terminology. A cell is one individual piece of one of these batteries. We don't have any place to measure cells, but that means it's a battery. One group of 6. The module, pack mean the same thing. So overheating conditions are really very important. They'll shorten the battery life, and batteries are thousands of dollars. So these are important codes. Here's some of the other codes we have. We're going to have temperature sensors. In this particular example, we got 3 sensors. Signal too low, signal too high. Boom. You know what to go to look for. What's going to cause the signal to be too high? Open circuit. Signal too low? Short circuit. And we got 3 different sensors. The battery module temperature signal has a circuit problem. It's a general catch-all. If it cannot make sense out of this, it's going to look at this. These are priority codes. They must be addressed quickly. Cooling fans. We got cooling fans for different manufacturers. They use different codes. If we have a problem with a cooling fan circuit, we're going to go find out. It should be able to turn on, turn off. Some are high side control, some are ground control. Look at your diagrams, figure out what you're looking at, and go fix this problem. They must be given priority. They're important. Now the other thing you need to know is these cells discharge if vehicle sits too long. Now this is not as severe as the manufacturers have told us. We've been told that these high voltage or hybrid vehicles must be run at least 30 minutes per month to prevent deep discharge. Well, we've seen some out of body shops that have been sitting for 3 months, and they're discharged, but they're not deep discharged yet. So this is a little bit of an exaggeration in our experience level. So if they're left unused, they will discharge. And you may have high voltage codes, and you can correct this very easily by taking the vehicle for a test drive for a few minutes, charging it back up. What are you going to look at? Look at scan data. When are you back in the 50 to 68% state of charge range? Now, the symptoms of a discharged high voltage battery pack are very important. Why is symptoms important? We got to react to things. What you're going to see in voltage, we're going to give you some symptoms. You'll also see repeated in temperature in other places. Acceleration performance may be poor until the battery is recharged. Now, why is this? Because we gave you a bunch of numbers early on in this section that says at 38%, it's going to quit using the electric motor. At that point, you drastically reduce performance. But at 40% state of charge, you're going to reduce the amount of power you get from the electric motor. That's also going to reduce acceleration performance. So an acceleration performance may be just a symptom of this, but there's also other obvious clues you'll be seeing when we try this. So 35%, we're going to shut the traction motor off. It's not even going to run. 40%, we're going to reduce power. So this is how we're trying to say you use scan data. When you see these numbers in your scan data, You know what's causing it. You have a low state of charge. Now the next question is, why is it discharged? Why isn't it charging? But you have a diagnostic direction. And this is going to be so important with hybrids. You get a diagnostic direction before you jump off in any direction. Now here's control module and battery module codes as a group. Let's start at the top. Battery energy control module. Problem. Is a general catch-all. You got to go work on the battery module. You got to go look at scan data to figure out what's going on. That's what that's telling you. Now, the second one down, P0A7D, high voltage battery pack, state of charge low. Oh, boom. You know what to look for. Go to scan data. Are we below 50%? Yes. Oh, we're low. How low? How big of the problem? Is it 35%? Don't let it get near that 6%. It shuts everything off. P047F, battery pack deterioration. Something's happened to the battery pack. Now we're going to take scan data and figure out how much deterioration. We don't throw the whole battery pack out. We're going to find the bad blocks and the bad bricks and replace those. P1AOF, hybrid control module, has disabled the hybrid battery pack. A fault has been detected. Now usually this is a loss of insulation. We're going to cover that in a whole separate section. We have scan data. You're going to have special test equipment for that. Another high voltage module deterioration. This is the 1400 series. So some people use the OA series, some people use the 400. 1435, charge discharge balance problem. That means for a certain amount of charge, you should be able to discharge. You're going to have to observe that as it charges and discharges. We're going to show you how to take it on a test drive and look at scan data. Why do we keep saying scan data? Because scan data is not dangerous. Taking high voltage battery packs out is dangerous. Individual battery module voltage deviation. We can look at battery module voltage by blocks, which is 2 bricks. Deviation means the voltage is not the same. Remember, they should be getting the same state of charge. All the current flows through all the batteries. If that's true, the voltage should be the same on all batteries if they're chemically the same batteries. If they're all chemically active equally, the voltage will be equal. Battery module deterioration. Battery module voltage deviation. Very much like 1446. Individual voltage problem on the module. Battery current circuit problem. So we're going to be monitoring current and voltage all through here. And again, it's to keep you out of the hazardous area. When we get in here, we can even get codes down to 3000 series that says a block. See those 2 bricks over there? A battery block is made up of 2 bricks. We call those 2 little gray things a brick. You take 2 of them together and they make a block. It's normally 14.9 to 15.2 volts. We can go look at these. And we've got 20 different battery blocks on here. Now you begin the idea. We've been talking about blocks and bricks. It's simply to keep your mind straight and get out of this. We got cells, we got batteries, we got bricks and blocks. We're reading scan data. We're looking at 2 batteries together. That's 14.9 to 15.2. We know that things are going to change if anything goes wrong. So here's some other things. Open circuits and current sensor problems. When we're looking at this overall system, we got a lot of modules to look at. It said, hey, in the orange circuit, there's a problem. There's an open between the high voltage battery pack and the battery control module. Now look, their battery control module is down inside the battery pack. When you get this code 3030, put on your rubber gloves, put on rubber sole shoes, no nails in them, all the safety stuff we talked about, because now you're going to get your hands on this 60,000 watt power source. I say 60,000 watts just as a number. It's really even higher. It's very high voltage. We want you to respect it. And the current sensor can be at different locations. This is a particular one, just showing you the one coming out of the battery. We'll look at the one coming out of the battery. This is for the high voltage battery circuit. We'll look at the current leaving the battery. We're going to measure it at other points as well. So all of this is going to work together with scan data, because you're not going to just use these codes. When we get this 3030, there's only so much we can see in scan data. We can go read voltages where we can. We'll show you how to do that in scan data. You can't do it all in one class, guys. You've got to spread it over time. We're going to read voltage at all different places, all these different modules. We're going to be looking at the voltage with scan data to keep you out of there, to make you as safe as possible.